one dependent. So we are starting with a method called Lagrange interpolation formula. Okay, it is not a one formula, it is depends on which strategy you want to use, but let's try to understand first Lagrange interpolation formulation, like what is the strategy behind Lagrange interpolation. So student, for that let's consider a data set defined like x naught, y naught, x1, y1, x2, y2, and continue till some last data xn, yn. We have done this many times. So let's say there is one data given to us and we write down them in the form of ordered pair. Obviously in practical application we do not have a data in ordered pair. We have a data in Excel or in a column wise, where one column is x coordinates and other column is y coordinates. But for the time being, assume that data is defined like that. So there, how many points are there? As we know that label start from x naught, so and end at n. So therefore there are total points. Therefore total points or data points or data set are n plus 1. Okay, because the last index is n, so last index is n, but data starts from x naught. So if I start counting, I will get n plus 1, because if I start from here 1 2 3, last will be n and plus 1 more x naught. So this is n plus 1. So how many points I have now? N plus 1. If I have this type of labeling starting from x naught, in some books you can find that the labeling start with x1, so then they are saying we have n points, but we want to say it like n plus 1 points. Why? You will understand shortly. Okay, so what I did so far, I have to define the Lagrange interpolation formulation, and for that I assume, let's say there are discrete data sets. How many? N plus 1. X represent independent, y represent dependent, and assume that there exists a functional relation between them, like there exists some function of this type, y equal to f of x, but we don't know what is that function is. Okay, but only we have a data, maybe we have recorded this data from any experiment or something, but we don't know. So that's why this is just a discrete data set. Now what we need to define the interpolation based on the Lagrange framework, how the Lagrange interpolation perform. To do that, let's uh, go for a little bit one one thinking problem. Okay, we have to think something, how the Lagrange will define interpolation technique. Basically interpolation is nothing, what we have to do, we have to find a function y equal to f of x that could be used to define this data set within the error. Okay, predefined error. So what we do, we will try to find a function that can represent this data. What does this mean? This means that if I put x naught in that function, I have to get y naught. If I put x1 in this function, so I have to get y1, and so on. The target is to find that function. Okay, but it has to be a reasonable accuracy. So Lagrange interpolation formula is basically a polynomial representation. What we do, we will try to fit a polynomial on this data set. But how? For every method, strategy is different. That's why we have a different methods. So what Lagrange do, it's a very simple concept. Listen, uh, for example, let's assume assume that we have only 2 points. So far we have n plus 1 in general, but for the time being assume we have 2 points. So how the data look like? X naught, y naught, and x1, y1. That's it. These two data sets, and we want to fit a polynomial. So on this data set, that we can find any value in between these two data sets. So if I go on a graph, so what I have now, it is x and this is y, and let's say somewhere there is x0 and somewhere there is x1, which is, and at x1 let's say I have answer y0, and x0 I have answer y0, and let's say here I have y1. Okay, so there is 2 points, one is this, one is this, and let's assume there is any point between x0 and x1, which could be anywhere, not in the mid or anywhere, it could be anywhere, like in mid is also okay, but I'm not deliberately not putting in the mid point. Okay, so it could be any point. Now my question is, if x0 has a y0 answer and x1 has a y1 answer, then what would be the answer at any point x? Keep in mind that x is any point between x0 and x1, it could be anyone. For example, x0 is 0 and x1 is 1, so x could be 0 0.7, 0 0.8 or 0.2, it could be any point, but it has to be in between these two. Now the question is, what would be the value? So you can say, okay, if I join these two lines, then I can read this point here, and what would be the y value, that would be the answer. But question is, do you really know that this would be a straight line? It could be any function. But what we do, we have some rule. Rule says that if you have 2 points, if you have 2 points, then the maximum polynomial that you can fit between two data set is of degree 1. So what's the point? If 2 points, if 2 points are there, then maximum degree that could be fit on the data is 1. So what's the relation? If you have 2 points, the maximum degree that you can use to represent this data set is 1. So degree 1, we all know degree 1 means polynomial of degree 1 means uh, straight line. For example, something like that, y equal to ax plus b. So if you have 2 points, the maximum polynomial, I mean with maximum degree, is 1. You cannot fit other than that. Okay, so 2 points are there, so you can fit a degree 1. So there is, so what will be happen if we have 3 points? Here I just give you idea with 2 points. Let's say there is another point x2. So I have 3 points then. Then according to the rule, it seems that whatever be the number of points you can fit only a one less than that. So if I have 2 points, then the maximum degree I can fit 1. So if I have a 3 points, let's say x2, there is somewhere x2, then I will get y2 somewhere. Then the maximum degree, I have 3 points now. So the maximum degree that I can fit is degree 2, because 3 points, if you have 3 points, the maximum degree is 2. If you have 2 points, maximum degree is 1. So one less. Number of points, as many as points you have to decrease it by 1, so that you know the maximum degree you can fit. Okay, keep in mind this word as well, is the maximum degree, because for example, if this y2 is not here, for example this y2 is here, so according to our rule we know that there are 3 points, so the maximum degree, the degree that I can use a polynomial is degree 2, but we know that these all 3 points are on a straight line, we can see that. Okay, so in this case, when we all the points are on a straight line, however there are 3 points, but we know that if we try to fit any polynomial on this data, it will be a straight line, it has to be a straight line, else there is some mistake in it. So that's why I use the word maximum, because if there are 3 points, which means that I can fit 3 points, so I can fit degree 2, I can fit degree 1, or constant, that is 0 degree. But maximum is one less than the number of points. So if for example, if you have 4 points, so the maximum degree you can fit based on the geometry of the points is 3. You cannot say that I have fit a data using Lagrange which is of degree 4 as well while having a 4 points. It's not possible. Okay, and not more than that. Then you will not get a unique solution. That's some point. Okay, so That's other thing. We are not interested in theoretical discussion. We are interested in the utilization of this function in this course mostly. Okay, so keep in mind, important point is that if you have n 3 points, you can fit maximum 2 degree. If you have 2 points, maximum 1 degree. If you have 1,000 points, and maximum polynomial that you can fit is of degree 999 something. Okay, so that's why now you understand why I have chosen to have n plus 1 points. Okay, now you can understand if there are n plus 1 points, so I know that the maximum degree that I can fit on this data is n. Okay, so if in different books you can find that there are n points, so if there is n point, then they have to claim that number of the degree that they can fit is n minus 1. So in our case, because we have assumed that there are n plus 1 point according to this labeling, then we can fit a maximum degree of n. Okay, so let me write down this point for you in general sense. It is direct point. We are not going to prove, but Lagrange this based on this strategy. So if there are n plus 1 points, okay, one thing keep in mind, is not necessary they are equidistant. They could be equal or unequal spaces, but if there are n plus 1 points, the maximum degree of polynomial is n. Okay, for example, if you have 4 points, you can fit maximum of degree 3. Okay, is so we cannot go more than that. Okay, so this is the one remarks. Okay, now understand, now we are going to understand the framework, how the Lagrange works, which is very simple technique. I already gave you idea that we have to find some function y equal to f of x, so that that could be used to interpolate the missing data. Okay, so how the Lagrange work, every method has its own strategy. So let's continue with the same point. Let's we have 2 points. Okay, so one point is here x naught, and the other point is somewhere there x1. Okay, so if you understand for 2 points, then we can extend it to any other point. Okay, student, let's so how do we define this 2 points? We know that there are 2 points, so maximum degree where we can fit is degree 1. We just learned that point. Okay, so what Lagrange do, Lagrange define the interpolation function like that. Okay, y equal to f of x equal to whatever be the function. Okay, so we can sometimes write y equal to, or sometimes we will write f of x equal to, depends. So f of x equal to something like that. So we have x naught, and then we also have y naught somewhere in y axis, and then there is somewhere y1. I'm not deliberately plotting them on a same level. It could be anywhere, it could be above, below, but there are 2 points only, and we don't know how we have moved from there to there, and x could be any value in between these 2 points. X can lie anywhere. Okay, so how to define the function based on 3 point? We know that the maximum degree is 1. So according to the definition, the Lagrange interpolation function is defined like that: y naught times L naught of x plus y1 times L1 of x. Okay, now I know you are confused what is L naught and L1, which is not mentioned anywhere. So these two functions are basically called Lagrange functions. What they are called? Lagrange functions. Okay, or sometimes, in fact, the best word is to call it Lagrange basis. We call it Lagrange basis. Okay, these function has a special characteristics. So let's say if the Lagrange function is defined like f of x, then this will become, I think it's better to write like that: L naught x y naught plus L1 x y1. Okay, you know that what is y naught and y1. If this is x naught, then the value of dependent variable is y0 and this is x1, and the value of dependent variable is y1. So these two quantities are known to you. So this is given to you. So these are known. The only thing is we have to understand what are these bases are, what they represent. Okay, so Lagrange basis has some characteristics. So if I want to understand this basis, it has some sort of a on and off mechanism, switch mechanism. How? First we understand L naught. L naught, I label it L naught because it is associated with this point, x naught. This is associated with this point. What does this mean? And obviously you understand I call it L1 because this is associated with this point. So L1 is associated with this point and L0 is associated with this point. It has something to do with these points. What they have to do is like that. L0 has this characteristic. L0 has this characteristic. If I put x0, this x0 here in place of x0, obviously one can clearly understand this is a function, Lagrange function, and it depends on x. So I can select any point here, but this function has this characteristic. If I put x0 here in place of x0 like this one, there must be some function which we don't know at the moment, but we will understand laterally. But it has to exhibit certain characteristic. Characteristic says that if I put x0 here, I will get 1, and on the same function if I put any other node, in this case there are two nodes only, one is x0 and other is x1. So if I put x0 in L0, I will get 1. This is its definition, how the Lagrange basis is defined. I already told you they have some sort of a on and off mechanism. So apart from that, any point you selected, any other node you selected, sorry, it will be 0. So if I know this function, I can put x0, then I can put x1 as well in that function. So if I put x1, it has to be 0. So for example, if there is x2 as well, 3 points, then if I put L0 x2, it also has to be 0. So that's why we call it, this L0 is associated with the x0. You understand now what the association means? Because it seems that at x0, this is alive, that is has a value 1, and on all other nodes it is dead, it is 0. So we can say it is associated with x0, it is associated with x0. Similarly, but question is how L0 look like, but you can understand now how the L1 has to behave. L1 has to behave like that. L1 must be 1 at x1 and it is dead, that is 0 on all other nodes. In this case there are two nodes, so it has to be 0 at x0. Okay, so these are the special functions that have a special definition. They are alive at one point and dead at other point. So how we will define them? So it is very quite simple. If we are having a live session, I will definitely ask you to think about it, any function that can have this behavior. Like if you put x0 in it, it will give you 1, and if you put x1 in it, on the same function you will get 0. So but here is a recorded lecture, but you can pause the video and think about it. Do you know any function of x that has this characteristic? Okay, so how the Lagrange function is defined, we have to keep in mind these two properties, that it has to exhibit these 2 points. Function should be same. So L0 x is defined like that. It is defined for x0, so it will be defined like that, x minus x1. So it is defined for x0, so there is no x0 on the numerator, divided by it has to be divided by some quantity. It has to be 1 on this point and 0 on the other point. Sorry, x minus x0, I made a mistake. So it is defined for x0, so it is x minus x0 divided by other point is x1, so x1 minus x0. Okay, so this is defined like that. Now what does this mean? X1 minus x0 divided by these two. Now what is the characteristic of this function is very simple. Oh sorry, what I'm doing, it is x1, it is a mistake, it is Okay, so this is x1. Okay, and the other is defined like that, x just x1, and then the denominator will be x1 minus x naught. Okay, so how this will be going to be work in this case is defined like that. I think there is some still a mistake in it. It will be hmm, so let's verify it. So if I put x naught here, I will get x naught minus x1, and in denominator it is also x naught minus x1, but in the opposite direction. That gives a negative value. So what I have to do, I have to define it like that. It has to be x naught and x1. Sorry, this is the proper form. X naught minus x1. Okay, so in numerator it is like that, and denominator is like that. Okay, now you can check. So if you put x naught in place of x, because I told you have to put x naught there, so x is this x. So if I put x naught there, I have to put x naught there. So x naught minus x1 divided by x naught minus x1, it will be cancel out, and I will get 1. Let me do it on the next slide. So L naught is defined like that, x minus x naught divided by x1 minus x naught. So let's check. So if I put x equal to x naught in this function, this implies L x naught equal to x naught minus x naught divided by x1 minus x naught. Okay, so which is 0 in this case. Now I think I I am okay. I made a mistake. This is x1. It has to be x1. Okay, so this is x1. So this will be cancel out. Let me do it again for you. It is not like that. Let's do it. Sometimes this happens. Oh, remove it. Remove it. Let me. I have copied wrong. I copied the other bases. I copied the base related to x1 point. Okay, so x minus x1 divided by x naught minus x1. So x naught should come first and x1 later. So x minus x1. Okay, so now check it. Let x equal to x naught. So if I put x naught there, so I will get L naught x naught equal to, which is 1, obviously cancel out, and this is 1. And similarly, if I put L naught x1, then I will get x1 minus x1 divided by x naught minus x1, which is 0, because they will cancel out. So it has this characteristic what we are looking for, the characteristic that L naught has to be 1 and L naught at x1 should be 0. This has this characteristic. So what I have to do now, I just need to put take this point function and have to put it here. Okay, I will put here. Then second thing is L1. L1 also has this characteristic. It is associated with this node, so it has to have this characteristic that it will be 1 at this node and 0 on all other nodes. So how should the x L1 look like? Obviously, if it is related to x naught, it is related to x naught. Then I have this construction. So I can see that in numerator there is no x naught. So if it is related to x1, then I can have a same idea that in numerator it will be x minus x1 divided by, now divided by what? Because there are only 2 points, so it is not going to be different. So what should I do? I have to subtract it again, x naught minus x1. Okay, so let's see. So if I put so if I put here x naught, so I will get x naught minus x1. Sorry, it has to be x naught. Okay, so if I put x naught there, I will get 0, which is correct, because L1 has to be, L1 has to exhibit the following characteristic. So if you put x naught there, it has to be 0, and if you put x1, it has to be 1. So if I put 1 here, So I'm not getting the correct solution, because based on that I define it. If I put here x1 like 1 x1, so I will get x1 minus x0 divided by x0 minus x1, which is not correct. I will get negative answer there. Okay, so I have to define it properly. So it has to be like that: x minus x0 divided by x1 minus x0. Now check it again. So if you check it again, it has this following characteristic. If you put x0 there, so x0 minus x0 is 0. Okay, and if you put x1 there, x1 minus x0 divided by x1 minus x0. Okay, so now what will I get? I will get 1 there. So this is how we have to define. So if I replace all the Lagrange function on these points, so what will I will get? I will get something like that: f of x equal to L naught. L naught is defined like this one. So L naught is x minus x1 divided by x naught minus x1 times y naught plus, I'm writing downward. So L1 is x minus x0 divided by x1 minus x0. The point that, and it times y1. There is no other point, so I will not do. Time that we have to consider is that, so if it is associated with x0, so there is no x0 in the numerator, and in denominator x0 subtracts the other point. This is associated with x1, so there is no x1 in numerator, and in denominator x1 subtracts the other points. Okay, this is how, and multiply by y0 and y1. So this is how the Lagrange function defined. Now why we have defined it like that? Because in Lagrange function we have to make sure that the data that we have is satisfied by the given function. So data we have is like that. Our data is x0 comma y0 and x1 comma y1, 2 points only. So this is the function related to represent this data. How? So if you put x0, you will see that you will get y0 exactly, because if I put x0 here, so we know that x0 minus x1 y x0, it will cancel out to 1. 1 multiply y0, it will be a y0 plus, and we know that this will goes to 0. This whole part goes to 0 because of the Lagrange function. We just know that Lagrange function has a definition at x1 it will be 0. So x0 it will be 0. So this part will be going to 0. So what we get, if I put x0 in this function, I will get y0. This is what we need. We need x0 at y0. And similarly, if I put in the same function, this is Lagrange interpolation formula. So if I put x1 there in place of x, so this will be cancel out, and here x1 minus x0 divided by x1 minus 1, so I will get y1. So what is happening now? If we use Lagrange basis like that, which has 0 and 1 mechanism on the nodes, and defined accordingly, so we can ensure that it will satisfy the solution at nodes. Okay, so we don't know what happened in between, but that is for sure guaranteed now that the solution must pass through the nodes. So nodes are x0 y0 x1 y1, and in the previous slide, with nodes I mean all these points. So we have to make sure that data passes through function. Lagrange interpolation function passes through all these nodes 100%. Okay, this is what we happening or going to happen here. Okay, this is what you have to keep in mind. So I mean to what the purpose is, that why we have to define like that is there is a reason behind it. We have to make sure that at x0 answer must be y0, and x1 and answer must be y1. But this is only for, this is Lagrange formulation for 2 points. Okay, when you have to use this thing only when you have a 2 points given to you. But if it is not 2 points, it is more than 2 points given to you, then you have to uh, use some other formulation. So what will happen with the n plus 1 point? But before to jump to n plus 1 points, I like to give you a Lagrange function for 3 points. So once you have a 3 points, we have discussed with 2 points, we have 3 points, then from there we can deduce it for n plus 1 points. Okay, Keep in mind that whatever with the points you have, you can fit a polynomial of maximum degree one less than that. So here I have 2 points, so I can see the maximum degree of x is 1 in either case. So if I solve it, because x0 and x1 these are the numbers, then y0 are the also numbers. So if I solve it, multiply, I will always get a straight line. I mean the polynomial of degree 1 here. So there are 2 points, so maximum degree is 1. So this property is also ensured in the Lagrange formulations. Okay, so let's continue further. If I have a for 3 points, for 3 points, obviously I'm not going to discuss it for 3 points or 4 points and 5 points and 6 points separately. It is just to introduce you, so I'm giving you the idea that how the Lagrange basis function are defined for 3 points, which means that I have these 3 points given to me and I want to understand, I want to define the interpolation technique. Okay, one thing is left which I have not covered. These are the 3 points, so we know that maximum degree is 2. Here I forgot to point out one thing. Okay, this data set is given to us and we have found this line, this Lagrange formula, but what we have to do with it? So now you can see that I already told you here that x could be any point between x0 and x1. Okay, so if you want to interpret at x0 you have a result y0 and x1 you have a result y1. Now you want to know uh, is there any point x here, and you want to know what would be the y value here. So what you have to do, you just need to put that x value here, so you can find the interpolated result based on y0 and y1. Okay, so this is the advantage of this function. If I ask you find interpolated reading at some other point, you just need to put that point in place of x, you will get that interpolated value. So you just need to read this function for any point. So now you have a 3. Well, according to the 3 points, Lagrange formulation will be defined like that. How we can define Lagrange formulation? Lagrange formulation will be defined like that. Because there are 3 points, so we need 3 Lagrange bases: L0, Y0, L0, Y0. Keep in mind. Plus L1, X is some function of X, Lagrange basis with associated with X1 node, Y1, L2, X, Y2. So you can understand now that if I increase the points, I have to increase the basis as well. So bases are also increasing. This is one of the drawback of the Lagrange method as well. You need to define basis in a very comprehensive way. So how would be the L naught look like? We have a clear definition. L naught is associated with X naught. This means that if I put X naught there, I should get 1. And if I put any other value, in this case, other values are X1 and X2, it has to be 0. Similarly, L1 is associated with X1. So if I put X1 there, I have to get 1. And if I put other nodes X0 and X2 in L1, I must get 0. You remember the word alive and dead. It has to be alive only on that node, that is, it has to get 1, has to reply, and 0 on all other nodes. Similarly, L2 is associated with X2 node, which means that if I put X2 in place of X, I have to get 1. And if I put any other value like X0 and X1, other nodes X0 and X1, it has to be 0. Okay, so what are the characteristics? If I just write down for you that L0 at X0 must be 0, L0 at X1, L0 at X0 is 1, and L0 at X1 is 0, and L0 at X2 is also 0. Similarly, what characteristic L1 has? L1 X0 is 0, L1 at X1 must be 1, L1 X1. You remember, associated. And L1 at X2 is 0. Similarly, L2 X0 is 0, L2 X1 is 0, and L2 X2 is 1, because L2 is associated with X2. So it has to be 1 on the nodes which are associated, and all other are 0. Now question is how L0, L1 and L2 look like in this case when we have a 3 points. So in this case, student, L0 will be defined like that. L0 of X Lagrange bases are defined like that. It has to obey these characteristics. Okay, so how we will define it? I just gave you idea. how many points are there? There are 3 points. So maximum degree that could be fit is degree 2. That is a square, the quadratic function that we can fit on this data set. So it has to be a quadratic, first of all. The second thing is that it has to exhibit these characteristics. Okay, so idea is like that. So I'm defining it for L naught, that is x, it is associated with x naught. So there will be no x naught in the numerator. So what are the points left then? X1 and x2. So it will be like x minus x1, x minus x2. So note that now we have 2 points. Why? Because x multiplied by x will generate x square. It has to be a degree 2 because I have 3 points. Divided by, so what's the rule? How I write down this? I am writing for L naught, which is associated with x naught. So in numerator there will be no x naught. So x minus x1, x minus x2. And in denominator you have to subtract x all the points from x naught. So x naught minus x1, x naught minus x2. Just copy it like that with x naught. Do not subtract x naught minus x naught because there is no 3. If you have 3 points, the basis will be consist of product of two functions, two linear functions. So now you can check if you multiply with this term, these are the numbers, so you will get x square. So Lagrange function is x square here. Okay, now check that whether this condition is verified or not. So you can check it like that. You do not need to define every time like that because I'm explaining you, so I'm writing these whole conditions, but you can write down direct cases. So check it now. If you put in place of x, x naught. So if you put x naught here, x naught here, what will happen? X naught minus x1, x naught minus x2. X naught minus x1, x naught minus x2. So they will cancel out numerator term and you will get 1. So this characteristics is okay. Now, if you put in place of x in L naught, x1, what will happen? So if you put x1 here, so it is x1 here, x1 here. X1 will minus x1, this will become 0 and they are multiplying, so overall this term goes to 0. Similarly, if you put x2, this will goes to 0, overall this term goes to 0. This means that L0 is 0 on all other nodes apart from x0. So based on that, you can also define L1. So idea was, if you remember, idea is that L1 is associated with x1, so x1 will not appear in the numerator. So what are the nodes left apart from it? Then node left is x0 and x2. So you have to define it like that, x0, x2. Why these two like that? Because we have to multiply so that we can get degree 2 polynomial, because there are 3 points. Divide by, rest is similar. Which node is missing? X1 is missing, so you have to subtract x1. You have to subtract all other nodes from the x1 in this fashion, like multiplying, and then you have to subtract, sorry, x1 into x2. Okay, so this you can verify it, it will hold like that. I'm just verifying this point. So if I put x1 here in place of x, so x1 minus x0, x1 minus x0 cancel out, x1 minus x2, x1 minus x2 cancel out, overall answer is 1. And similarly, you can define the L2. So I'm writing L2, L2 is associated with x2. This means that in numerator there will be no x2. So what I have left, x1, I have left with these two, divided by, in denominator I have to subtract all the nodes from x2 because this is defined for x2. Or other words, just replace x with x2 in denominator. Okay, this is how you can verify this property. Okay, I'm just verifying for 1. So if I put x2 in place of x, I will get x2 minus x0. In denominator is x2 minus x0, cancel out. X2 minus x1, x2 cancel out. So overall answer is 1. So it is certain. These are the Lagrange bases. So Lagrange basis has a characteristic 1 and 0. Okay, so it is 1 and this on the node which is associated with, and the 0 on all other nodes. So if I have to define the Lagrange interpolation formula for 3 variables, 3 points, so I just need to put L0 here, L1 here, and this one here. So I will get the interpolating formula. Okay, and which ensures that if I put in interpolation formula x0, I will get y0. If I put in the same formula, I will put x1, I will get y1 exactly. And if I put x in place of x2, I will get y2 exactly. So this is how this is defined. Similarly, student, now you can understand if I have 4 points. So one base is added in L3. and L3 needs to be defined, but also because there are 4 points, the maximum degree is 3, so there will be a 3 products involved in numerator and denominator each basis. Okay, so this is how you have to define for basis 3 and 4. So let me write down it for general, in a general sense. Okay, we know that how many points we have n plus 1 points. Okay, so n plus 1 points. So if I have n plus 1 points, how we will define it? For n plus 1 points, so if you have n plus 1 points, this means that maximum degree that you can fit is of degree n, degree n. So how do we define it? Lagrange function. So f of x, we know that what will we can find it. So here, if there are 3 points, the last node is 2, basis is 2, so it is L0, L1, L2. So here I have n plus 1 points, that is point, and the maximum last point has an index n. So this means that I have to sum I equal to from 0 to n. Okay, what I have to sum? Li x yi. Now you can check. If you open this sum for n plus 1 points, so the maximum degree is n. So if you open this term, you will get the same. For example, if there are 2, n is 2, so you will get L0 x y0 plus L1 y1 plus L2 y2. So you will get the same. This is defined like this term. Now question is how to define Li, because this is the Lagrange base and it depends on the number of points. So how do we define it? We know by heart that there will be a n basis, but how do we define them? How we have to define? So we have to define it like that. This is I index. Okay, so Li x is defined like that. This symbol I will explain. This is called pi product symbol. This symbol of x minus x minus x I divided by xi minus xj. Okay, and this is carried over j, ith index, provided that I is not equal to j. Okay, so what does sorry, this is also j. I made a mistake. This is also j. This is j. And what is j? I will explain to you. Uh, this is j. So this is j. The index, and this product is carried over j. J goes to 0 to n, but what is this product first? Friend, if you remember, if you have a sum sign, which is here as well, so if you have to sum something, you can write down, okay, I0 to n means it is summing x0 x1 till xn. This is how you have to define the sum symbol. But if you have a pi symbol defined like that, I 0 to n, for example, xi, this means that these terms has to multiply each other. X0 into x1 into x2 till xn. They are not adding, they are multiplying. So that's the difference. Similarly, if y is defined, this is overall, like on numerical board. So this is one term. So this means that these terms are multiplying. So over J naught. So here J naught, J naught. Okay. And whatever the base you are using, you have to keep the I index fixed. This is I, this is J. So this product is running on J. So there will be a J terms that are multiplying from J0 to Jn. But what you have to make sure that I sorry, j cannot take any value equal to I. It is not equal to I because we remember that that j cannot be appearing on the numerator. So you can start multiplying the terms, but you have to make sure that whatever be the value of I is here, index is here, you cannot use that value. Okay, so this is how we have to define the basis in general sense. Okay, so I think it just maybe some student will not find it comfortably. So how I have write it in a this is basically a compact notation or mathematically compact notation, which is explained exactly because the point is that it is depending. So sum is running, product is running over j 0 to n. Okay, and we want to ensure that we can take j 0 to n any value, but j must not be equal to I. Okay, if j, so this is running on this thing, I remains fixed. If for example L1, so this will remain x1 throughout, but this is changing. But we have to make sure that we are not going to subtract x1 from x1 because j cannot take any value equal to I. So this is how Lagrange. So for each I you have to define one basis like that, and they will multiply and open. Okay, so this is how we have defined the Lagrange for general sense. This is general points. I hope you understand the concept behind it. So if you have 5 points, 6 points, 7 points, does not matter. You need to define Lagrange, and this is why Lagrange function is computationally involved. You have to perform the computation. Once you have a computation, it's not a problem. You just need to replace it. A Lagrange bases are ready. And once you have this function, you just need to replace the point, whatever the point you want to use to interpolate the data set. Okay. So let's discuss one example with a small example. That once you understand that example, then uh, rest is just a procedure of application based problem. So let's discuss that part, and the other part that in which I will explain to you Newton forward backward. Maybe we will not able to solve the example of these two formulation. Once we have this formula, we will continue with the supplementary lecture in the next time. Okay, so let's solve one example related to Lagrange interpolation formula. Example. If you like to have a break, you can have it. Okay, student. So, for example, consider the following data and find the value at x equal to 1. I'm not giving application problem. Let's any data. So this data is given to us. Okay. This is x values. These are y. It could be time, current, or anything will be defined in the form of data. So there are 3 data sets only. So at 0, at 1 we have to interpolate, so we forgot to note down the reading at 1, and then we have a reading at 4. Let's say the readings are 0, 4 and 16, for example. Okay, although I hope all of you understand which function is this following. 0 squared is 0, 2 square 4. So we all know that data is following exactly this polynomial. But let's say we don't know in real time, we don't know which data is following what, but I deliberately selected a data that is following something so that we can verify also whether we are getting the same data or not. So it is not mentioned any method, usually it is not mentioned, but you have to decide yourself. So Lagrange interpolation can be applied to equally spaced data as well and unequally spaced. So here the data is unequally spaced. How I know that? So if you select x and find the difference of the two consecutive values, 2 minus 0 is 2, and 4 minus 2 is 2 as well. Sorry, this is equally spaced data. But for example, it is 5 here. So 5 minus 2 is 3. So it is not equally spaced in this case. But here data is equally spaced. So Lagrange can be used. Okay, this is extra point. Lagrange formula can be applied to equally spaced or unequally spaced data. Okay, why I pointed out this thing here? Because if method is mentioned, then it's not a problem. You have to apply that method. But if method is mentioned, then you have to think and the later stage whether Newton forward will work here or Newton Lagrange. So if the data is unequally spaced, we usually prefer Lagrange polynomial. But keep in mind, in either case, whether the data is equally spaced, unequally spaced, you have to perform a calculations because Lagrange is computationally involved. So idea is there is some point x which is missing, which is x equal to 1, and we have to find the value. We have to find y. So basically what we have to do, if this data is represented by a certain function, let's assume we don't know that function, so we want to find f1 basically, which is not known to us, using Lagrange. So let's solve it using Lagrange. Using, you have to explain your method. You using Lagrange interpolation formula. Okay, this f of x is usually a Lagrange interpolation formula what we are going to do, and this L0 L1 are called Lagrange functions or Lagrange bases in other terms, so do not confuse this thing. So this whole f of x which we have defined here, this f of x is Lagrange, based on Lagrange strategy is called Lagrange interpolation formula. But these LIs are called Lagrange functions or Lagrange bases. So solution, Lagrange interpolation formula. So Lagrange interpolation formula, how does it works and what we have to do here? Let's go through. So how many points? We have 3 points, so we have to use 3-point formulation. We have 3 points. 3 points. Question is how I know that? Obviously we have 3 points, x0, y0, x1, y1, x2, y2, 3 points. So 3 points formulation would be like that: f of x equal to summation I running from 0 to, we have 3 points, so not 1 2, so n is 2 in this case, li x yi. Okay, that's not a problem for us. And where this is interesting, let's see how many of you remember, where lix is defined like that: pi products, that is terms needs to multiply, which term? These terms, x minus xj upon xi minus xj. This sum runs over j from 0 to n, and provided that j cannot take any value which is equal to I. Okay, so this is how. So this is the Lagrange formulation. Sorry, here n is 2. So n is 2. Here n is 2. We know that n is 2, so we are not going to write it in a general sense. We know it. So, and we're running from j to 2. Okay, so this is defined like that. So in expanded form, this will become like that. When you open the sum, this will be like that: L naught x y naught L1 x y1 L2 x y2. This is the Lagrange formula 1, where L0 x L1 x and L2 x are Lagrange basis, Okay, this is you have to find. So if L0 we are computing, let's discuss this. This means I has a value 0, so we have to run j 0 to 2, but such that j cannot be equal to 0. Okay, so I remember it, just I have done this before as well today, so let's do it like that. But we have other technique, that was a fancy way of writing in mathematical term, but we have a other way to remember. L0 is associated with x0. This means that in numerator x0 will not appear. there will be no x naught in numerator. So x minus x1, x minus x2, y2, because x into x will generate x square, and there are 3 points, so maximum degree is 2. So that's okay, that's fine. And in denominator, because this is associated to x naught, we have to subtract all the points from x naught. So in denominator only that appears. So this is how we have to memorize. But the fancy way of writing is this. Okay, this is the mathematical way. Similarly, you have to define all the bases. So L1 of x, L1 is associated with x1. This means that there will be no x1 in numerator. So whatever left is this. And then in denominator, you have to subtract x, all the points from x1. Similarly, L2x, you have to define all the bases general form first. L2 is associated with x2, which means that there is no subtraction. There will be no x2 in numerator. So whatever left is divided by x, and then you have to subtract all the points from x2. Okay, so these are the bases. So we have to fill all the data sets there, and then we are ready to interpolate the data. Okay, so how we will do that? Also, because x naught y naught appears, x naught y naught is 0 0. It is 0 0. It is not, because it is not or not. It could be any value, but it is like that. So, and x1 y1 is 2 4, and x2 y2 is 4 16. This is defined like that. Okay, so just replace it, you will get the formula ready, and then you have to replace them on this position. Y0 is 0, y1 is 4, and y2 is this. So you have a Lagrange formula ready for interpolation. So now let's do it. We can do it directly as well. F of x L0 is associated, so it will be like that, x minus x1. So what is x1? X1 is 2, x minus x2. What is x2? X2 is 4, divided by which node we are writing? L0. So L0 x0 is 0. It is very easy for us now. 0 minus 2, 0 minus 4. We can write down, but we know. And y0 is 0. So this basically, this term is going to 0. There is no need to simplify that term. Okay, L0 y0 plus L1. Now what is L1? L1 is this term, x minus x0. X0 is 0, so x minus 0, and x minus x2. X2 is 4, divided by x1, that is 2. 2 minus 0, 2 minus 4, multiply by y1. What is y1 here? Y1 is 4. L1 y1 plus, you know that, x minus, it is L3 L2. So L2 is associated to x2, so there will be no x2 in numerator. So it will be x0 and x1. What is x1? I forgot. Right, x1 is 2, divided by x2, that is 4 minus 0, 4 minus 2, and this whole will be multiplying with y2, and y2 is 6. Y2 is 6. So should keep in mind this whole is multiplying by 6 as well. So because of this 0, it does not always happen, but in this case it is 0. So this whole term goes to 0. So you have f of x equal to 0 plus this part. You need to simplify this thing. So 2 minus 0 is 2, minus 2. Okay, x, it is, you just need to simplify. I'm not going to explain this. X into x4. So it will be become x into x minus 4 divided by 2 minus 2 minus 4, and there is a 4 on top. This will be cancelled out, plus x minus 0 This is x minus 2 divided by 4. This is a bracket. So 4 minus 0 is 4 and 4 minus 2 minus 8, and there is a 6 on top this thing. So it will be cancelled out to certain degree. That is 4, 3. Now you have to simplify the other terms. In interpolation, there is no need to simplify, but in general, I am giving you an idea to simplify it. But if you do not simplify, it's also fine. What does I mean? If you keep it like that, this is x minus 4, this minus 4, so minus 1 is there. This is minus 4, so this will become minus 3 upon 4 x minus 2. So this is the, if you keep it like that, it's also fine. This is basically the function that you fit, but in general it is recommended to simplify it so as much as possible. But for us, because in our problem the answer target is to find the interpolated value, so if we know the function, we just need to put x equal to 1. So if I put x equal to 1 here or here or in a simplified form further, I will get the same answer. It does not matter. But sometimes we need to know the function, so in that case we have to simplify. So it is easy example, so let's continue and simplify it so that I can verify as well, because if you remember, I told you I know this data is following a certain function which we already know. So I also want to verify that whether we are getting that function or not. Okay, so that's why I'm simplifying, but there is no need. I'm repeating again. If interpolation needs to be done, just replace x equal to 1 or whatever the point it is asked to you. Just replace it here and you will get the answer. So let's simplify further just for our sense. X square plus 4x minus 3 by 4. I have a doubt on this part. Let's see, minus sorry, this is 4 minus 3 by 4x square plus 3 by 2. Okay, so we are getting this representation, and data is following exactly a polynomial of degree 2. I think there is some mistake then, and definitely the mistake must be happen 0 minus 2. That's okay. So x minus x naught, x minus 4. Is it correct? Yes. X naught and x2, x1 and x2, and x naught and x1, x1, x2, x naught, x2, and here x naught, x2. This is also correct. 0 minus 2, 2, and 4 minus 0, 4 minus 0, and 4 minus 2. That's also correct. So this is defined like this one: x2, x naught, x2, x1. So x naught, y naught, x1, y1, 2, 4, and x2, y2, 4. Oh, okay, I got the mistake now. Since I put 6, it is not 6, it is 16. That's why I was wondering why it is not. It is 16, not 6. Okay, so this mistake happens sometimes. So this is not like that, but data could be anything, so you have to be aware of. So this is not 4. So let me correct this thing. So I have found a mistake in the calculation. Maybe you have no, you are going to a recorded lecture, so you already notice it. So that's good. And I think I need to redo the calculation, because that expression has created confusion in my mind, because I'm expecting some other results, because data is following exactly something which I already know. So Lagrange function must give that function that data is following exactly. In this case, it is not necessary always, but in this case it is. for sure, because data is also satisfying on the node and also on any point. So it must be, so this is part 0 and this is the same thing again. So this is this part and this is the same. So this will be give -8 and it is 16 there. So this will be cancel out like that. This will be 2. Okay. So whatever left here is, this is minus x into x minus 4, and this is minus as well. So it is 2. So this will be -2 into x minus 2. Okay. Now simplify it. Minus x square plus 4x minus x square plus 4x minus we have to multiply this thing, x square minus 2x. Simplify further. Minus x square plus 4x minus 2x square, and this will be plus minus minus plus. I think I'm so making again mistake. This should be 8. 4 minus 2 is 8. Why is minus 8? There should be no negative sign. Okay, so there will be no negative sign. I don't know why I'm making so many mistakes today. 2 times of x square, this is plus, and this is 4x. Okay, so oh sorry, minus 4x. 2 into minus 2 minus 4x. So this minus 4x will cancel out with this, and this 2x square and minus x square. Final answer would be x square. So the Lagrange function in this case is x square, which is correct because this data is following x square function. I already wrote down somewhere there. So you can check it. If you put x, you will get 0. If you put 2, 2 square is 4 and 4 square is 16. So data can be represented by this interpolating formula, which is correct. Now we have to interpolate the data as well. So interpolation needs to perform at x equal to 1. So f of 1 is wherever x is, you have to put 1. So if you put 1 here, you will get 1. So answer is 1. So your interpolating result is 1, and in this case this is also the exact result, but it will not always happen. But in this case it is the exact result as well. So what I was saying, if you have to perform interpolation, there is no need to simplify. You can put x1 here as well. So you have to solve this thing, you will still get 1. But when you has been asked to fit up polynomial or fit a function on the data as well, so you have to simplify it till the possibly. Okay, without making mistakes that I have done here. Okay, so this is the interpolation. So you know the answer now, it is 1, which is obviously true because we know the function. But if you don't know the function, you can still predict the value correctly. So I have done two things here. One, I have defined the Lagrange function to you, and I also explained the process of finding the interpolation based on Lagrange. And then also I selected an example in which the data is known to you which function it is following. So in this way you have verified the concept as well. Yes, that result you are getting is correct as well. So this strategy works all the time. But you can clearly see for such a small problem we have to do so many computations. This is the only drawback of Lagrange method. You need to perform calculations. However, they are very good in accuracy, and it depends on the local nature of the points. So if there are n points, you have to define accordingly. If you have 2 points, you have to define accordingly. So this is what I was referring in the initial case. So this is how the Lagrange works.